Welcome, everybody, to Energy and Climate, How We Got Here and Where We're Going, with Rick Allmendinger. Rick is Professor Emeritus of Earth and Atmospheric Sciences at Cornell University. He is by training a structural geologist and has spent most of his career working in the Andes and the Western United States. Nonetheless, he is a New Hampshire native by birth, and his family have owned property in the Chocorua Lake Basin for nearly 100 years. His first professional geology job was mapping glacial deposits and bedrock units in northeastern Massachusetts for the USGS under the direction of Jean Boudet, who later became state geologist of New Hampshire. At Cornell, he taught courses in structural geology, regional geology, and energy and climate change. He is also a very good friend to Chocorua Lake Conservancy and this community. He leads wonderful geology walks each summer where we learn to see the landscape differently and also understand more about climate change, past, present, and future. He'll be leading a walk on July 13th. He's also the creator of the Chocorua Map app, which you can access via the CLC website or in the Apple App Store. The app includes trails at Mount Chocorua and on CLC conservation land, set into a geographic and cultural context. And I am very appreciative whenever I have the opportunity to learn from Rick. I'm happy you're here with us tonight. Thank you.
Well, thanks, Juno. And thanks to everyone who's signed on for taking time out of your evening to join us here tonight and to listen to this presentation. As Juno said, I spent my career mostly on the geology side of the Earth and Atmospheric Sciences, and worked in various energy-related things and so on, particularly towards the end of my career, including, as she mentioned, teaching courses in energy and climate change. And these two are actually the flip side of the same issue. Our energy issues are our climate issues and vice versa. And we need to understand, how energy plays into that to understand what we need to do to deal with the dilemma that we find ourselves in today. So everybody probably knows that 2023 was a year of climate records in the Northeast, and indeed climate records throughout the world. In our particular part of the world, up here in Carroll County and so on, the yearly average temperature in 2023 was 3 degrees Fahrenheit above normal. And we received, I don't really need to tell you this, we received way more than our average precipitation, somewhere between 125 and 150% of our average precipitation. So climate, of course, would be a talk all on its own, and you've undoubtedly read a whole bunch of articles and seen TV shows and so on, many with very dire warnings and so on. And I'm perfectly capable of telling you all about the gloom and doom that faces us with climate change and so on, and scare you with things like positive feedbacks and loops and so on. But I think we're all maybe a little tired of what has come to be known as climate doomerism. So what I'm going to do instead in this talk is focus on the flip side of the climate issue, and that is the energy issue. This talk will be in 3 parts, and I anticipate it'll take somewhere around 35, 40 minutes to go through, which hopefully will leave time for questions at the end. The first part is going to be a historical perspective, and that's how we got to where we are today and why humans are addicted to fossil fuels. This is really a story in 3 exponential-like curves that I'll show you and we'll go through in the first part of the talk. The second part of the talk will talk about energy transitions. So we know we need to abandon fossil fuels, but what comes next and what are the trade-offs? And finally, the third part of the talk will focus on what individuals can do to make a difference. Okay, so let's get started. So I'm a scientist, and scientists think in graphs and so on. So I'm afraid you're going to have to suffer through a whole bunch of graphs in this talk, and hopefully they won't be too onerous to go through. The bottom line is on almost all the graphs, time will be on the bottom axis, and some factor, in this case, concentration of CO2 in the atmosphere, will be on the vertical axis. The actual numbers here, particularly on this axis, really, it doesn't matter too much what they are. What I want you to focus on are just the trends in some of these curves. All right, so in this case, what we're looking at is the extraordinary record of atmospheric CO2 from ice core records in Greenland and Antarctica. And the different colored dots are just from different ice cores that cover different time spans. We're seeing everywhere from today, down here at the right hand, back to 650,000 years ago. So quite a ways back. And during that entire time, atmospheric CO2 never exceeded 300 parts per million. Now, in the last 50 years, plotting on the same curve, it does this. Basically, on this scale, a vertical spike going up now today, well above 400 parts per million of atmospheric CO2. If we just blow up the last 2,500 years of this history, we see the curve looks like this. And this is our first exponential-like curve, where it goes flat for a long time or very gradually increasing, and then all of a sudden it almost goes vertical. Some people call these hockey stick-like curves because of the shape similar to a upturned hockey stick and so on. So in this case, what we see unequivocally is that the rise in atmospheric CO2 during the last 25 years, this big vertical spike, essentially correlates with the start of the Industrial Revolution. That is to say that this spike in CO2 is anthropogenic. That is, it was caused by humans. There's really no doubt about that at this point, that this is a human-induced phenomenon. Now, one thing that's kind of ironic is that we've known about the physics and chemistry of the greenhouse effect for about 165 years. And thus, even at the very start of the Industrial Revolution, physicists and chemists were already defining how greenhouse gases like CO2 and other greenhouse gases would affect the climate. So we've actually known about this effect for a long time. And there's, in terms of physics and chemistry, there's absolutely nothing mysterious about the greenhouse effect. It's well known, well accepted, not debated by any serious scientist. All right, so this is exponential curve number one. Exponential curve number two, you also know about, and that is this is world population since the beginning of the Common Era, 0 AD. And I was born in 1953, and the world population at that time was 2.5 billion people. Today, of course, it's over 8 billion people. And it's kind of stunning to realize that the world population has tripled during my lifetime. In some ways, it's even more stunning that the world population has increased by a factor of 2 in the time that I've been alive. And well, let me put it this way. The increase in world population during the time that I've been alive is larger than the entire growth of the world population from 0 AD to when I was born. That's the nature of exponential curves. And to put another emphasis on it, since the beginning of this century alone, world population has increased by 1.7 billion people. And by 2050, it's projected, world population is projected by the UN and the US Census Bureau to be around 9.4 or 9.5 billion people. Bear in mind, by the way, that a child who is born today is likely to be alive, is only going to be less than 30 years old in 2050, and they're likely to be alive at the end of this century. So many of these things that we're talking about that are playing out are going to be during their lifetime. All right, so this is exponential curve number 2. The third exponential curve you may not be so familiar with, and that is the increase in worldwide per capita GDP, or the GDP per person. Now, this figure is a common, although imperfect, measure of standard of living. What we can see here is an extraordinary increase starting around the mid-1800s and increasing, again, coinciding with the Industrial Revolution. And the only reason why we could have this really remarkable increase in worldwide standard of living is thanks to fossil fuels. The first coal, and then oil and natural gas. And we really, there would be no other way, and there were no other energy fuels through most of this time to produce this remarkable spike, which is all the more remarkable because worldwide population is increasing so rapidly during the same time. And this is a factor of 10 increase in worldwide standard of living. All right, if you have any doubt that GDP and energy consumption are inextricably linked through economy, here's an example from the last 50 years history in China. You can see GDP per person is the blue dashed curve, and energy consumption is the yellow curve, and they track each other pretty much almost exactly. And this increase in slope here of this curve, rapidly increasing the per capita GDP in China, is the Chinese economic miracle, which, among other things, literally lifted tens of millions of Chinese out of poverty during the last 30 years or so. For this reason, the satirical news site The Onion published this headline about 10 years ago. New report finds climate change caused by 7 billion key individuals. Now, like most satire, good satire, it has more than a germ of truth to it. And that is that the sheer numbers of us, combined with the modern conveniences that we all enjoy, are fundamentally what is responsible for climate change. But you have to pay the piper sometime, and nothing comes for free. And the cost in this case of this prosperity are global CO2 emissions. This graph shows you the global CO2 emissions separated out by region from 1965 down here up until 2022, the latest year for which data are available. And you can see a substantial increase, a tripling of CO2 emissions over that time period. But what's more interesting in some ways about this curve is it's an extraordinary record of major economic and cultural events in the world. For example, this decrease right here corresponds to the global recession in the late 70s and early 80s, produced by the Arab oil embargo that people who are my age and so on are likely to remember. This orange band right here corresponds to the Soviet Union in this part, and to the countries that make up the former Soviet Union in this part. And the collapse of the Soviet Union was accompanied by an economic collapse, which resulted in halving, essentially, their CO2 emissions. The Chinese economic boom, which I've already talked about, is this increase in slope right here. This divot is the 2008-2009 recession, and this one here is the pandemic. So during the pandemic, when we all were restricted to home and not traveling anywhere or doing anything, the drop in CO2 was about 5%, or a little, about 5%, I would say. So that gives you some idea of how a profound event has even then a relatively minor impact on our CO2 emissions. So in 2022, China and India were responsible for 31% and 7.5% of global CO2 emissions. Europe, the dark green band here, was responsible for 11%. And North America, including the US in particular, but also, of course, Canada and Mexico, was responsible for about 17% of those emissions. But what I'd like to point out is that outside of the Asia Pacific region, CO2 emissions actually peaked in 2007, and they've been gradually decreasing. The reality is that the only place they've been decreasing is in Europe and in the US, because all of these areas, Central South America, former Soviet Union, Middle East, and so on, and Africa, they are actually stable or gradually increasing. But the decrease and the magnitude of use in Europe and the US is enough to mean that outside of Asia Pacific, CO2 began decreasing in 2007 and has pretty much increased at a very gradual level during that time. There's also some suggestion that it might be leveling out even in globally, and not just ignoring India, China, Indonesia, etc. But lest we feel too smug about the fact that we're reducing emissions and we only produce 17%, and these countries collectively produce way more than we do. If you look at per capita CO2 emissions, here in the United States, we still produce twice as much CO2 emissions per person as in Europe and China and Japan and so on, and 6 to 8 times as much emissions per person as in the rest of the BRIC countries, such as Brazil, India, Indonesia, and so on. So we don't necessarily have that much to be proud about based on that last curve. So this is global energy consumption by fuel now, where how do we produce energy? And you can see the big 5: coal, oil, natural gas, nuclear, and hydro here. Now let's put on the renewables that we read so much about and so on. That's geothermal, that's solar, and that's wind. So you can see here, you can at least see these. When I started giving these talks back in the early 2000s, the impact of these renewables was practically invisible on this graph. At least you can see them now. To look at it another way, carbon-based fuels still account for about 83% of global energy consumption. Nuclear and hydro account for another 11%. And the renewables on which we're placing so much faith currently account, or in 2022, accounted for 6% of global energy consumption. Well, how fast are these various different fuel types growing? So we can look at the rate of utilization. How quickly are we increasing the use of some fuels or decreasing the use of others? And these graphs over the last 30 years or so, since 1995, I haven't shown you the renewables yet. This just shows you coal, oil, natural gas, nuclear, and hydro so far. The Chinese economic miracle is this big bump in coal right here at the peak of that huge increase in utilization. China was building a new coal-fired power plant once every 7 days somewhere in the country. This big drop in nuclear that you can see here was the direct result of the Fukushima earthquake and nuclear and tsunami and nuclear disaster, and many countries abandoning their nuclear after that event and so on. But most of these are just muddling along between 0 and 3%, most around 1 to 2% increase in utilization per year. Now, if we put renewables on here, oops, come on, there we go. They're outstripping, the rate of growth of renewables is outstripping all of these others. It actually peaked about a decade ago at close to 18% increase year over year on a 3-year running average. But for the last decade or so, it's been muddling along here between 12 and 15%, something like that. So, if you have you're starting a business and let's say you're starting a business mowing lawns and you have one client and then you find another client, you've just increased your business by 100%. Whereas a company like Microsoft or Apple or so on, it's impossible for them to increase 100% because they're already so big. And unfortunately, this curve, as good news as it is really not that good news. Whoops, there we go. If we go back to 2019, the last year before the pandemic, the actual absolute increase in utilization of fossil fuels, which are here muddling along at 1 to 2%, was actually +7 exajoules, whereas the renewables, I keep hitting my mouse button, sorry about that. The renewables increased at +3% at that same year interval. In other words, we're still increasing the use of fossil fuels in absolute terms at a rate about double that of renewables, which is not good news for going forward. All right, let's skip over or on to energy transitions. We know we need to drop fossil fuels. How are we going to do that? Well, let's talk about, go back and take a historical perspective. And it's amazing to think about that, again, here we go from 1800 all the way up to 2022 on this graph. It's amazing to think about that until about 1850, about the only fuel source available was traditional biomass, burning of traditional biomass. This is burning wood and peat and things like that. We barely even used coal back then. But as starting about 1850, coal begins to ramp up quickly as driving the Industrial Revolution. Then oil comes in and eventually begins to be more important than coal, and then natural gas, and so on. Another way to look at energy transitions is to look at a graph like this, in which we plot the percent of total energy produced as a function of fuel. So for example, in 1900, here on this dashed line, about 50% of our energy globally was provided by traditional biomass burning, and about 50% from coal. And oil and natural gas are just barely beginning to be utilized in 1900 or so on. If these were normal energy transitions, we would expect over time for coal to diminish and be replaced by a less expensive and more efficient fuel like oil, and then oil to diminish to be replaced by another less expensive and more efficient fuel, and so on. In other words, we'd expect these curves to do something like this. But that's not actually what we see. On this graph, I show world population, by the way, as the dotted red line. And what you can see is that starting around 1950, right about the time that world population starts going into overdrive, all of these energy sources begin to level out. And they begin to level out because what we did is we added new energy sources simply to meet the increased demand, which was driven by increased population, and not because we were replacing less efficient, more polluting fuels with more efficient, less polluting fuels, and so on. You can see that well in this graph, where again, population plotted as the dotted red line. And now I've stacked all of the fuels together here, and you can see that the uptick in population and the uptick in fuel consumption match each other extremely well. Excuse me. It's important to realize that with the exception of whale blubber, humans have never abandoned a single energy fuel. In fact, today, we burn more traditional biomass, primitive traditional biomass, than we did in 1900 or 1800 or any time previously. So what we need to do now is abandon not only a fuel like whale blubber, we need to abandon the fuels that currently provide 83% of our energy consumption, all while we add another 1 to 2 billion people to the planet. That's a tall order. So what's that transition going to look like? Well, here's the graph that I showed you before, from 1965 to 2022, the different fuel types and different gaudy colors here and so on. And so I'm going to shrink this graph and extend this time axis out to 2050, which is the magical number where we want to be carbon free. And it looks like this. These go to zero. Many people would like nuclear to go to zero, and I'll have more to say about that. Hydro, the planet's actually at relatively close to peak or maximum hydro capacity. And that's because most of the major rivers on the planet already have dams on them and so on. And so this is what the transition has to look like to green energy. Now, let me assure you that this is technologically possible to do, but it's a profound transition, the likes of which humans have never accomplished in the past. But let me return to this nuclear question for a minute. About 10 years ago, 4 of the most esteemed climate scientists in the world wrote an open letter to the environmental community. And here's some of the key things they said. I'll only read the part in yellow. They stated, in the real world, there is no credible path to climate stabilization that does not include a substantial role for nuclear power. So let's try and understand a little bit more about why they said that. And to understand that, you need to understand the different types of energy going forward in terms of intermittency versus continual energy source, what's commonly known as baseload energy. Intermittent sources are those that vary with time, and the variation is out of our control. We can't control when night happens, and when our solar panels will be ineffective. We have little control over when the wind blows. We can predict when the tides go, but they slack tides and so on are all variable. And the variation in these intermittent sources, there's no guarantee that the variation will coincide with when we as a people and as an economy need energy. Baseload energy, on the other hand, is always available. It's currently provided mostly by fossil fuels, but also by hydroelectric, nuclear, and in a few specialized areas, geothermal. Now, we'd like to get rid of fossil fuels, of course, to be carbon free. Hydroelectric doesn't have the capacity to ramp up and replace fossil fuels. Geothermal electricity from geothermal is only available in a fairly specialized geologic settings, such as Iceland, parts of the Western US near active volcanoes, and so on. And that leaves for baseload energy, nuclear for electricity, and geothermal for heating. Now, the less baseload capacity you have, the more you have to rely on energy storage technologies. And the main problem with this is that large-scale energy storage solutions remain lacking. And I'll get into that in a minute. But let's talk about cost for a minute. You have heard this phrase probably, that solar and wind energy are now the cheapest sources of energy available. And that's absolutely true. To put in a solar farm costs way less than to build a nuclear power plant, and even significantly less now than to build a gas-fired power plant. But that comes with a significant caveat. It does not include the price of energy storage. And as we do away with baseload energy sources, energy storage will become increasingly important. The reality is, for example, today, if you have solar panels and you do net metering, you are essentially using the fossil fuel powered electrical grid itself like a battery. That is, when your solar panels produce excess electricity, you sell that electricity or you send that electricity to the grid. And when you need electricity, when your panels aren't producing electricity, the grid sells you back electricity, often from non-green sources like fossil fuels and so on, sometimes from green sources, but not always, and so on. At least for residential systems today, complete battery storage options at least double the cost of solar panel installation, and so on. So batteries are going to have to come down a lot in price, to make intermittency not a problem. The other reason why batteries are problematical has to do with a concept known as energy density. Energy density is the amount of energy that you can get out of a fuel as a function of its volume here, or as its mass down here, a quantity known as specific energy. What you really need to know on this graph is that up and to the right is better. What you can see here, these are fossil fuels, and this explains why fossil fuels have for so long been so important in our economy? And that is because there's no other naturally occurring, abundantly available fuels which have as high energy density as fossil fuels. Energy density is the reason why gasoline, which is this dot right here, when you put gasoline in your car, it gets better mileage than when you put E85 gasohol in your car, which is this dot right here. And that's because gasoline is a more energy dense fuel than gasohol is. Batteries are the yellow dots down here. They have extremely low energy density compared to these other fuels, which is why the current crop of electrical vehicles are both heavier and they have less range than traditional internal combustion engines. So 20 gallons of gasoline weigh about 125 pounds, and you can go 500 or more miles in a modern internal combustion engine on those 20 gallons, unless you're driving a big heavy SUV, but let's assume you're driving a Toyota Corolla or something like that. The battery in a Tesla weighs 10 times as much as that gasoline. That is, it weighs about 1,200 pounds, and you can only go half the distance, 200 to 300 miles. And the reason for that is the low energy density of batteries. But a potential solution is also on this graph in the form of these green dots over here. These are hydrogen. And one potential solution to large-scale energy storage is to use our intermittent sources when they're available to produce green hydrogen by electrolysis of water, which can then be stored and used as a fuel to meet baseload energy demands at times when the sun isn't shining or the wind isn't blowing. That is, use hydrogen as if it were a type of battery. Another concept to be familiar with is energy footprint. This is the amount of power per given area here. And you can see different green energy sources here. Wind energy is somewhere, it's very variable depending on the area, but it's on the order of 2.5 to 3 watts per meter squared for a traditional wind farm. Solar photovoltaics in Northern Europe and in places like New Hampshire here are about 5 watts per meter squared. In deserts at low latitudes where you have much better sun, say the Mojave Desert in California or the Sahara, what have you, they produce about twice the power per square meter, and concentrating solar plants in desert regions produce more still. Unfortunately, if you compare this to, say, a nuclear power plant, there's no comparison. Here is the energy footprint of a nuclear power plant compared to the green energy sources. Now, to illustrate the significance of that, here's our fair state of New Hampshire. Here's the Massachusetts border down here, and the Maine border with New Hampshire here. Here's our 18 miles of coastline. And many of you know that there's a very controversial nuclear power plant at Seabrook, located right there. And that nuclear power plant produces about 1.2 gigawatts of power in approximately 1 square kilometer area. In fact, this little red dot has been exaggerated so I can show it to you. To produce the same amount of power from a wind farm operating at 25% capacity factor, you would need to cover 480 square kilometers. That area is equivalent to the area of all of Lake Winnipesaukee. And that is the impact of having these diffuse energy sources such as wind and to a lesser extent solar, is that much more of the land surface will need to be devoted to the energy, the generating capacity. So it sounds like I'm a real fan of nuclear, and I'm not really. As a geologist, I appreciate better than most when people say that some of the waste isotopes from nuclear power plants will remain dangerous for geological time periods. And nuclear is very problematic in other ways. For example, it is undoubtedly the most expensive of the currently available fuels that we have. But concern about nuclear, if you go just based on the historical record, may be overblown. This is a figure from the data site at Oxford University called Our World in Data, which I highly recommend. And they took a look at what are the safest and the cleanest sources of energy. And and when they measure safest by the number of human deaths which are produced per terawatt hour of electricity produced. And not surprisingly, our three fossil fuels, natural gas, coal, and oil, not only are the dirtiest in terms of greenhouse gas emissions or pollution, but also they are the most dangerous in terms of the death rate associated with those sources of fuel. Nuclear actually plots down here pretty much equivalent to wind and solar, both in terms of death rate, and this includes deaths associated with Chernobyl and with Fukushima, and in terms of low carbon emissions, and so on. All right, let's segue to the third part of the talk now, which is what can an individual do? When you survey individuals about what they can do to make a difference, you often get results like this. Recycling is generally highly thought of as a good strategy for preserving energy, changing your light bulbs to LED light bulbs, buying green energies, switching to an electric car, and so on. But here's what actually makes a difference. Oops. So this is, for example, if you owned an SUV and you gave it up completely, you would actually save 3.5 tons of CO2 equivalent emissions per year. Now, most of us can't give up our cars, particularly in rural New Hampshire, but if you were to become a vegetarian, you would save 2 tons of CO2 emissions per year. Just skipping one transatlantic flight, you would save 1.5 tons of CO2 per year. That's about equivalent to buying green energy. And as Tamworth is, I understand, exploring the community power model that Warner, where I live now, has also recently adopted. You don't even need to put solar panels on your house, because in those community power things, you can specify the portfolio of green energy that you would like, to have provided for your energy. So you can go the easy route without a very expensive capital outlay at the beginning to put in solar. Switching to electric cars or going from electric car to car free, you also save more than 1 ton of CO2 per year. The rest of these things certainly help, and they're important. You should do them. There are good reasons for doing them, but you should not do these and feel like you're making up for not doing stuff up in this part of the curve. So, change out your light bulbs. That's a great thing, but that's not going to give you an excuse to not invest more in green energy or become a vegetarian or whatever. There are variations in all of these. For example, it turns out that this is a vegetarian. This shows you the change from eating beef to becoming a vegetarian. If you smaller animals have a smaller impact in CO2 emissions and so on. So you don't have to completely give up eating meat, but simply eating more chicken and things like that, fish, etc., would go a long way, would realize most of the savings in this bar right here. So let me list a few additional things that I think are important. This one is a no-brainer, of course, but it needs to be in the list. You have to vote. And sometimes the right choice will be one that will hurt your pocketbook. Not everybody can afford that, and that's perfectly understandable. But if you can afford it, if you want to put the climate first, some things that you may be asked to vote for may take some money out of your own pocket. Second, you should advocate for training of people in our public schools, community colleges, and universities to support green energy development. If we are successful in transitioning to wind and solar and so on, we're going to need more people in these fields who know what they're doing. Third, you need to understand in a very fundamental way that climate change respects no boundaries. And so what China does affects us, and what we do affects China. Unfortunately, a small nation like Micronesia, what they do doesn't really affect any of us at all. To bring this home a little bit, if, just say hypothetically, Massachusetts wanted to get rid of their fossil fuel-fired power plants by bringing clean, carbon-free electricity from Hydro-Quebec down through New Hampshire, that is going to benefit New Hampshire simply because Massachusetts will be producing less greenhouse gases and so on. Finally, you need to understand that renewable energy will require large amounts of land compared to what we're used to. And sometimes that the land which is best suited for green energy development is land that we cherish as wild and undeveloped. In my 45 years of doing geology around the world, one of the things I've learned is that most land on Earth is special to someone or some group of people. And NIMBYism is an enemy of green energy development and deployment. Unfortunately, we're already seeing this. These two maps, which are both animated, they'll stop soon, I promise, recently published in a series of stories in USA Today. And these are showing the number of counties in the country that are either have a moratorium or are making siting regulations so onerous as to outright ban wind on the left and solar on the right. Now, Southeastern California and Arizona and Nevada here would be wonderful places for large solar developments, and yet they've been banned throughout this area here. The high plains in the middle of the country are spectacular wind sites, and yet they're being increasingly banned throughout Nebraska, Kansas, Iowa, and so on. Now, you might think that this is all, a conservative politically conservative trend, but not completely. I don't think anybody would call Vermont and Connecticut, conservative states, and yet they have essentially an all-out moratorium on wind development in their area. Now, we all appreciate our own backyards, our own scenery, and consider them to be of extreme and special beauty, and consider them to be precious, and so on. But unfortunately, everybody else in every other part of the community, part of the country and the world thinks exactly the same way about their own backyards. And we need to come up with some way that's equitable for siting these installations that is not completely based on the privileged getting what they want. So one more thing is, what interventions get people to adopt greener habits? That is, how do you convince people to adopt greener habits? And this comes from an article that was recently published in the Proceedings of the National Academy of Sciences. And it pains me as a lifelong educator to see in this article, which is a summary of tens of other published articles and so on, that education is the least effective way of getting people to change their minds. The most effective way? Seeing what your neighbors do. That is, if we model good behavior, that is by hanging out our wash to dry, or investing in solar panels or electric vehicles, or signing up for more green energy in our community power options and so on, it's much more likely that our neighbors will follow suit. Okay, so let's wrap up. Where does this leave us? So we're nowhere near the rate of deployment of carbon-free energy sources that we need to become carbon-free by 2050. Wind and solar are incredibly important, but because of their diffuse and intermittent nature, they're unlikely to be the sole solution. And because of very low energy density and reliance on scarce strategic minerals, batteries are not necessarily a good option. One of the areas that I do research in is in northern Chile in the Atacama Desert, where much of the lithium, about 50% of the world's lithium, comes from right now. And I can tell you that extracting lithium is not impact free. So humans have never produced an energy transition as rapid and as profound as what we need now. And humans don't like change, but I think they'll eventually be spurred to action by a combination of climate refugees, rising sea level, and extreme weather events. In fact, I only half jokingly say that the people who are politically most concerned about immigrants should be the ones who are the strongest supporters of green energy development, because we haven't seen anything yet in terms of the flood of climate refugees and immigrants that countries in the increasingly northern parts of the northern hemisphere or southern parts of the southern hemisphere will experience as the world warms up. Unfortunately, the climate system has a lag time of about 2 decades built into it. And that, for example, the CO2 that we're producing today won't actually impact the climate and the temperature, et cetera, for about 20 years from now. So by the time the skeptics are convinced, we'll have lost decades of precious time, and remediations will be much more costly. But there is also good news. One is that we are either at or close to peak CO2 emissions globally, as I showed you everywhere outside of the Asia Pacific region, the CO2 emissions are stable or decreasing. We actually have all the energy technologies, solar, wind, geothermal, and yes, even nuclear, in hand for a carbon-free future. We don't have to invent anything to become carbon neutral. We don't have to wait around for hoping that some new technological advance will come along to make the impossible possible. We actually have sufficient land and coastal waters, more than sufficient land and coastal waters available to deploy those diffuse energy technologies. We just have to get used to doing it. And green hydrogen is one of the better alternatives for large-scale energy storage from intermittent energy sources. So we have to make some profound and difficult decisions, and those decisions need to be guided by data, not by emotions, special interests, or conspiracy theories. Now, if you're as old as I am, you remember the cartoon strip Pogo. And this was a poster that Walt Kelly produced back around the time of the first Earth Day. As he said, we have met the enemy and he is us. Yes, there are corrupt, self-interested politicians, there are rapacious fossil fuel companies that aren't doing the right thing, and so on. But until recently, humans' collective desire for a higher standard of living was only possible with fossil fuels. But today, we actually have the technology in hand to be carbon free if we're willing to spend the land and the dollars to do so. And in terms of dollars, the impacts from not doing anything will probably be greater economically than the impact of switching to green energy fuels. Let me end by simply saying, if you're finding all of this talk, either my talk or everything you read in the news depressing today, a good book which is actually well worth reading is this book which came out in January of this year by Hannah Ritchie, titled appropriately, Not the End of the World. And she takes a rather upbeat attitude towards how we can actually be the first generation to build a sustainable planet. And it's well worth your time to read it. Hannah Ritchie is the chief data scientist for Our World in Data at Oxford University. And by and large, she knows what she's talking about. And people like Bill Gates and others have noticed. Anyway, so that's my talk, and I would be happy to entertain questions now.
Thank you so much, Rick. Yeah, thank you so much.